let's continue our discussions. In the last lecture, we were talking about, we began by talking about the performance analysis of the standard array decoder, which I have also referred to as the syndrome decoder. And then after finishing that, we started a new topic and we were dealing with a new class of codes. These class of codes are called convolutional codes. And basically what we are going to do in the beginning is just look at different ways of describing convolutional codes, okay. And then after that we will settle upon one viewpoint, and I am doing this all initially through a simple example which I pointed out as a prototype example, and I am going to run the descriptions right into the decoder. So, the sequence in which we describe convolutional codes is a little different from block codes, but perhaps is the more natural sequence for a convolutional code. So, let us just quickly run through our last time's lecture here on the pad. So, we started by looking at performance analysis of the standard array decoder, and which meant that we were interested in knowing how it performs in terms of bit error and code word error probabilities, and we also wanted to know, if I have the standard array in front of me, how can I actually compute these quantities for any given code, and we handled that. Then the next topic that we went on to is convolutional codes, and these codes are codes that have description in terms of an encoder of this type. Okay. And so the encoders of this type, and we pointed out that this is properly viewed as belonging to the class of tree codes, and after talking about tree codes we actually said we took care of some details here, and we said that amongst the class of tree codes they have finite memory, linear and time invariant. And then I said, well, you could also talk about the generator matrix of a convolutional code in the same way as you could in the case of a block code, except that it turns out to be not very useful, because it's inconvenient to actually use it because it's semi-infinite. What is more natural is a polynomial / power series viewpoint, and we were getting into that. So, towards that I started defining what it means to talk about the field of formal power series. So, the field of formal power series is the collection of all objects of the following form. You are taking expressions of this form, and when you look at this you should not start worrying about convergence, because in algebra the word formal means we are just going to treat it as an object, and we are going to say you can manipulate this object by adding objects and multiplying objects in a certain way, and that is enough for our purposes. We are not really going to evaluate it, at least not yet. Okay. So, you do not have to worry about convergence at this point. And the other thing to note when you look at this expression is that on the one extreme the exponents go off to infinity, on the other extreme you are permitted to have a finite number of negative exponents. So, that is what the symbol D here represents. And then I made the comment that all field axioms are satisfied with the possible exception of the multiplicative inverse, because it is not quite clear how one would actually go about computing the inverse. So, let us pick up from that point. I am going to cut this page and paste it onto my current lecture. Okay. So, for our recap, I will just say that we completed studying the performance analysis of the standard array decoder. Then we moved on to study convolutional codes, and here I introduced the encoder, I introduced the semi-infinite generator matrix, okay, and then I believe that was all that we had looked at. And towards the end I said that you really need to know, you need to study formal power series and polynomials. And the field of formal power series in D is the set of all expressions of the form k goes from minus d to infinity, a sub k d to the k, where the a sub k are drawn from a field. Okay. So, perhaps I will be consistent and use the same symbol. And I said that if you want to check whether this is a field, it is fairly easy to check that when you look at this together with plus in this, it is easy to check that under plus is an abelian group. How do you define addition? Because supposing, for example, I wanted to add 1 plus d cubed plus d to the 7 plus d to the 19 and so on, and I wanted to add this to, let us say, d4 plus d5 plus d6 plus d7 plus d8, then you would add it in the usual way. You would add it term by term. So, the result would be, the result of adding this to this would be 1 plus d cubed plus d4 plus d5 plus d6 plus d8 plus d19 and so on, because it so happens that the d7s will actually cancel. So, addition, it is fairly straightforward. You would add them just as you would add polynomials. And multiplication is not very different either. So, what you see here in this figure is a preview of something to come, but let me just defer that. So, I am going to introduce a blank page here. So, you can also check that as far as multiplication goes, that under this operation, this actually satisfies the axioms of closure under multiplication, and that multiplication is associative, and that there is an identity element, namely which is the formal power series 1, and then multiplication is also commutative. So, the only question that you might have in your mind is, what about inverses? And towards that, let me just take an example and show you how one would actually compute inverses in this case. So, supposing you had to compute, let us say that you needed to compute d plus d cubed and you wanted the inverse of that. Okay. So, you can write this as 1 upon d plus d cubed which you can write as 1 upon d times 1 plus d squared, and this 1 upon d becomes d inverse divided by 1 plus d squared. And now I will just tell you as an aside, that any time you have an expression of the form 1 plus g of d, where this thing here is a polynomial in d that is divisible by d, then you can write 1 upon 1 plus g of d as 1 plus g of d plus g of d the whole squared plus g of d the whole cubed, and so on going up to infinity. And you might ask, well, why is that the case? Well, it is just because if you multiply this by this, you will actually get 1. So the proof, in case you are curious, is 1 plus g of d into, now let me again take use of our technology here, put this whole thing here, put it down here, so if I take this and multiply it by 1 plus g of d, then you will see that there is a lot of cancellation and you will actually be left with 1 at the end, okay, because you will get a g of d term by when 1 multiplies g of d, you will also get a g of d term and g of d multiplies 1, and the 2 will cancel, and it will happen for all the successive terms, so that this is equal to 1, and hence you actually computed 1 upon 1 plus g of d inverse. So getting back to our situation here, so let me put a bracket. So this was an aside, all of this. Now we are interested in computing d inverse upon 1 plus d squared. Therefore, d inverse upon 1 plus d squared is equal to d inverse into 1 plus d squared plus d to the 4 plus d to the 6 on up to infinity. So this is d inverse plus d cubed plus d5 and so on. So that is how you would compute inverses. Now you see that it would have been impossible to compute the inverse if you are not allowed a finite number of these negative exponents. So that explains why you have d to the minus 1 here. Okay. All right. So now hopefully with that you are convinced that in fact you are convinced that this set over here, the field of formal power series, is in fact a field. Now what we are leading up to is an alternative description of the code. Okay. Let me just see if I can take care of that. I think in the process I have added a few blank pages, and let me see if I can get rid of them. Okay. Okay, good. So I think I have what I want. So for the encoder that we had looked at previously, and I think I may want to bring that back from our earlier lecture. So let's see if we can get back our earlier lecture here. Yes, here we go. So I'd like to bring back this particular page. So let's cut and paste that. Okay, so here we have our encoder that we had looked at last time. And what I want to do is I'd like to describe this in terms of polynomials. Okay, this is our encoder, just so that you refresh your memory. There's one input, over here, and there are two outputs, and the input output relationship can be written like this. And I'm going to introduce two power series. So our goal is describe the convolutional encoder in terms of a polynomial generator matrix. And so what I'd like to say is that in fact it's possible to describe the convolutional code in this way. Just say that it corresponds to the following polynomial generator matrix: 1 plus d squared, 1 plus d squared. So this is a 1 by 2 matrix. Now okay, you might be a little bit surprised by that. What do you mean by a matrix when you are putting terms 1 plus d squared? Aren't you supposed to put real numbers in a matrix? But actually you can define matrices over any field. That is, you can have a matrix and you can put numbers from any field in it. We are typically used to either putting real numbers or complex numbers, especially when you are studying linear algebra, but actually you can put elements of any field. Here in fact we are going one step even beyond that, because we are saying we are actually going to put down elements in the matrix that come not even from a field, but actually from the collection of polynomials. Okay, the polynomials actually form a ring, and we saw that earlier when we were discussing rings. So we are taking matrices over the ring, but that's fine. All your matrix operations are valid. Okay, so this is your polynomial generator matrix, and we will typically abbreviate this and say and refer to it as a PGM. So this is the PGM for the code. So how do we actually arrive at that, and what does it mean exactly? So to see that, you'll have to look closely at these equations, and if you look at it closely enough, it looks like you're actually convolving the input with a certain sequence of finite length, and that is what is giving you the output. And as you know, if you have a convolution in the time domain, you can represent it as a multiplication in the transform domain, right? Like for example with Z transforms, and your D is very similar to is playing the role that Z plays in the Z transform. Okay, so let's define, to just make that a little bit more formal, we'll define u of D to be the sum uk dk, k goes from 0 to input. So, this is the power series associated with the input to the convolutional code. So, you can think of this, if you like, as the input power series. And now, as far as outputs go, there are actually two outputs, and so we will associate a power series with each one of them. So, V1 of D is defined. So, all of these are definitions, defined to be the sum k goes from 0 to infinity V k1 d to the k, and then you have V2 d okay. So, we have our three power series defined, and now it is merely a matter of converting the time domain expressions to, so let us call this okay. So, we will say that converting the time domain input output relation given in 1 to the D to the D transform domain we get that V1 of D, V2 of D is equal to U of D 1 plus D plus D squared 1 plus D squared. Okay. And this is what we called our polynomial generator matrix. Now, this equation is similar in a sense to the equation that describes the relationship between the message symbols and the code symbols in the case of a linear block code, because after all this code is a rate k by n code where k is 1 and n is 2. Okay. So, you can see for this reason this is a 1 by 2, it is a 1 by 2 matrix. So, you have the n in some sense, whereas in the case of a block code you have n output symbols, you have n output streams and k input streams. So, you can see why one would want to refer to this as a polynomial generator matrix. Now, exactly how do you go from the time domain expressions to the frequency domain? I am sure most of you can actually fill it out on your own given your background in transform theory, but we will actually consider the general case a little later. So, I am going to defer it to that point. So, right now let us just accept that this is another description of the convolutional code. Another one which might have already occurred to you is that you can actually describe this in terms of a finite state machine. So, the finite state machine, of course, it is a reference to the encoder So, you see that the encoder has 2 shift registers, and since each shift register can store either the value 0 or 1, in a sense this finite state machine has a memory of 4, or in other words it has 4 states. So, we are going to write down these 4 states here. So, these are the 4 states, and now we are going to represent transitions now from 0 0. So, a word about the notation. So, when I write 0 0 here, what I mean is that this is u k minus 1, and this symbol here is u k minus 2. That is, so this collection represents the past 2 symbols. Represents the past 2 symbols. So, here if I get 0 0 and let us say that the input is a 0, then I am going to remain in this state. Okay. And on the other hand, if my input is a 1, I am going to transition to 1 0. So, I am going to follow the convention in describing convolutional codes, that when the input is 1 you actually draw a solid line, if the input is a 1 you put down a dotted line. So, this means that the input is 0 and a dotted line means that the input is equal to 1. All right. So, let us get back to our diagram, and so now from 1 0, if the input is a 0, then you would actually go to 0 1. If the input is a 1, 1 continues here. Here if the input is a 1, 1 continues, remains in the same state. On the other hand, if the input is a 0, you go here and so on. So, this is then the finite state machine. Now, but apart from this, one would like to also record information about the corresponding output. So, for that let me do the following. I am going to put down a table here, and the table is going to have it's going to have so here okay. So, you have the input, the state, and you have the output, which is V1 and V2, which represent the output. there are 4 possible states that the finite state machine could be in: 0 0, 1 0, 0 1, 1 1, and in any state that it is, the input could be 0 or 1, 0 or 1, 0 or 1, 0 or 1, and the output, if the input is 0, the state is a 0, then the output is 0 0, and if the input is a 1, the state is 0 0. Well, you can figure it out, because so for that you have to just go back here and just look at these expressions here. So that means that you are going to sum the past 3 symbols to actually get the first output, and the current input and the input 2 instance prior to get the second. So if you keep that in mind, then since these represent the previous input and the input previous to that, the first output is obtained simply by summing all the 3 symbols. So in fact, let me just make this a little bit clearer, and I will write down the state 2 times, because I just do not want to confuse you. So this is the state is 0 0 here, and so on. So if the input is 0, the state is 0 0, the output is 0 0. To get the first output, you always add the 3 symbols. So that is 1 1 0 1 0 0 1. The second output you actually get by adding the first and the third symbols, because the current symbol and the symbol 2 instance prior to that. So that in this case would be 1 0 1 1 0 1 0. Okay, so these are your outputs. So in the finite state machine, what I would like to do is I would also like to record these outputs. So if I just remember what the outputs are corresponding to a state and an input, I can actually fill in the finite state machine that we had earlier. So you can check that the outputs in this case, so let me put that in red so that it stands out, are 0 0 1 1, and here it is 1 0 0 1 1 1, excuse me, this should be 0 0, this is 0 0, this is 0 1, and this is 1 0, and this is 0 1. Okay. So you can check these on your own, or it is just a matter of applying this table and putting in the entries from that here. Okay. Now there is another very popular representation of the convolutional code, and it's really originates from the finite state machine, because what you do is you take the finite state machine and say that I am going to make a distinction between the same state at different instants of time. Okay. So I am going to unfold the finite state machine in some sense with respect to time, and that leads to the trellis. So here I have actually shown the trellis of the convolutional code. I am thinking that maybe what I should do is just show you how it evolves, and then we will come back to that picture if necessary. So we begin, let us say we begin at, so I am going to have 4 rows each to represent each of the possible states. So let us get that straight. So I am going to write 0 0 here, then I am going to put down 1 0 0 1 and 1 1. So these are the 4 possible states. Let me say that I initially start out in state 0 0, which is usually the case, and then at the next instant of time. So here is my starting state, And going back to the finite state machine here, if I am in state 0 0, I can either stay in the same state or I can transition to 1 0. Okay. And so I am going to, and I go from 0 0 to 0 0 when the input is a 0. So I put that down, and similarly if the input is a 1, I go to 1 0 and so on. So now I am going to complete the figure by drawing in the transitions corresponding to the next input as well. When I am in state 1 0, I can either, if I get a 0, you should actually visualize the 0 as coming in from the left and bumping this older symbol out. So the 1 0, because the 0 comes in, shunts this and transforms this to a 0 1. If a 1 comes in, it becomes a 1 1, so it will transition here. Okay. So this is the transition to 1 1, and this was what we had earlier, and so on. Okay. So this is the what the trellis will look like, and now I am going to bring in what I had drawn earlier. It is at a slightly more advanced state of completion. So now let us complete that. I will try to be careful because there are lots of lines that we are going to have to draw. I will try to keep them as clean as possible. One thing I am realizing is that this pen is first of all not very good at drawing dotted lines, and on the other hand, since we have color, I can actually use color to distinguish input and output. So let me try to do that instead. Okay. So let's use color here. So I'll put okay. Now also I need to shift this entire diagram a little bit to the right. So let's do that. Perfect. So now I have space to actually label the different states here. So this will be 0 0, 1 0, 0 1 and 1 1. Okay. So I am going to represent, let us use blue, let us use this dark blue for a 0 and this light blue for a 1. Okay. So I think that might make this an easier diagram to draw. So then I know that if I am in state here and I get a 1, I am going down here. So let me draw all of those transitions. Okay. And then if I am in state 1 0 and if I get a 0, if I get a 1, I am going to transition down to a 1 1. If I am in 1 0 and I get a 0, then I am actually going to go down to a 0 1. Okay. So I have taken care of transitions originating from the first two. If I am in state 0 1 and I get a 0, I go there. If I get a 1, then I am going to transition to from 0 1 if I am in state 0 1 and a 1 comes in, I am going to transition to 1 0. So, let us represent that. Okay. So, we have taken care of 3. So, that leaves the one at the bottom. If I am in state 1 1, the input is a 0, I am going to go up to 0 1. On the other hand, if I get a 1, I am going to remain in the same state. Okay, now I think the only thing that we need to check is what is happening towards the end of the trellis in this region, and here I think I may want to make some slight changes. I would like to actually remove these states because I want and for reasons that will become clear a little bit later, I want to start on the all 0 state, but I also want to end on the all 0 state. It is a matter of convenience, it is not really essential. Now you might ask, why is it that you want that? It is a matter of convenience, and it also makes the analysis easier. In practice you might do things a little bit differently, but it simplifies the way one thinks about the code. So, the way you actually bring the convolutional encoder back to the all 0 state, and that is quite obvious, you look at this the generator here, and all that you need to do is you need to bring in 2 trailing zeros to bring this to the all 0 state. So, that is what we are going to assume. What that means is that in this trellis, so what this trellis represents is the succession of states that the finite state machine goes through as a result of feeding all possible input sequences to the finite state machine. So, in that sense, every path in this trellis represents a possible input sequence. Now, since the last 2 symbols are 0, that means I should only have black everywhere over here. All right. So, I want to bring this back. So, the only way I can get to the all 0 state is if in the previous state I was either in the all 0 state itself, and let us go back to the finite state machine to make that clear. So, the only way to get back to the all 0 state is if I am in the previous instant either in the 0 1 state or the 0 0 state. So, I am going to make use of that. So, the 0 1 state is out here in the bottom. So, that is the only state I am going to keep here, because I know that the input is going to force it to the 0 1 state. So, we will just draw only this state, because no matter where you are here, the next this penultimate stage you are either going to be here or here, because you know that your input is going to be a 0. If you were at 1 1 and you get a 0, then you will actually move here. If you were at 0 1, then you will go if you were at 0 1, you would go here. If you are at 1 0, then you will come down here with a 0. If you are at 0 0, you will stay over there, and finally over here you will come here. So, you can see that in these last 2 stages all the lines are black. All right. Okay, I just realized that what's happening is that the blue and the black don't show up very differently on your screen. So maybe it's worth taking a second to change all these blues to a 1 so that they really stand out, so that you don't get confused. Okay, so we'll just take a second to do that. Okay, so here it seems to want to select all of these at one time. So maybe I should just cut this and draw this again. So let me do that. Okay, so all right, so this is yeah, so I guess I'm going to have to work a little harder to change the remaining ones. So let's take care of that in the old fashioned way. Okay, now if we've done things correctly, between any two levels we must have an equal number of zeros and ones. 1, 2, 3. Yes, so I think 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. Okay, so we have, and towards the end we are only putting in zeros. Okay, so now I think the trellis is a little bit more clearer. So what this trellis helps you visualize is all possible input sequences, and now what we'd like to do is we'd like to also use it to represent output sequences. Okay, and the output sequences we are going to take from the finite state machine, and in fact we already started when we so let me do this on this part of the trellis here. We know that if you are in state 0 0 and if your input is 0, then your output is going to be 0 0. Okay, so let me also represent that. Let's see which color will look good here. Perhaps I should let's see if green is visible on your screen. Yes, it is. Okay, so we'll represent the output in use green. Now so the output is 0 0 here, 0 0 here, and you can verify it's 1 1 here, 1 1 here, and so on. So let's go back to the trellis and label all of the edges of the trellis, and so recall that a solid indigo is a 0 and a solid red is an input. So this is at the input. Now as far as the output goes, I am representing that in green here. So let's fill that in also. And the outputs here, in fact let me do one thing, since I feel that in the next lecture I am going to call upon this trellis several times. I am going to actually copy this page and keep it as a spare, because I am certain to need it in our next lecture. Okay, so I am going to save that here. Okay, let's try that again. I'm going to select page, copy page, insert new page, paste page. Okay, good. So I have the trellis the way I want it for next time, and for now I'll feel free to write on this version. So let's complete this now. So this is, the outputs are 1 1, from 1 0, when you transition with an input of 1 to 1 1, the output is okay. So here we go. So this is the table that we'd actually like to use when you are in state. So let's try to remember this. When we are in state 1 0, when the input is 0, your output is 1 0. 1 0 with an input 0, the output is 1 0. So this thing here is a 1 0. And you can similarly verify that this output here is 0 1. That when it is in state 1 1 and the input is 0, the output is 0 1. So here I will have 0 1, sorry, when the input is 0, I will have 0 1. So this is 0 1, 0 1, 0 1, 0 1, 0 1. But on the other hand, when the input is a 1, the output is a 1 0, 1 0, 1 0, 1 0. Okay. So let's see. I think we've the only other there are 8 transitions within a segment. So we've labeled 1, 2, 3. When you are in 0 1 with a 0. When you are in state 0 1 and you get a 0, the output is 1 1. So let's put that in. So this is a 1 1 as well. And the only other transition we need to worry about is the transition from 1 0 to 0 1. So when you are in 1 0, when you are in 0 1 and you get a 1, the output is 0 0. You are in 0 1 and the output is 0 0. So this transition here is 0 0. So with this, and we are almost coming to the end of our lecture, we have another. So this involved a little bit of work, but I think we will put this to good use in the lectures to come. In this is a graphical representation of the code, and what you can see in this graph is that for every input sequence there is a path in the graph that leads from start to finish. Okay. So here this is your start node, this is your end node, and every code word spells out a path in this trellis. Now if you can also see the code words which are part of the code, because associated with every path you have a sequence of output symbols, and that represents the code word. For example, if the input sequence is all zeros, then the output sequence is also all zeros, and that is your code word. On the other hand, if your input sequence is all ones except for the last 2 zeros, then your output sequence is 1 1, 0 1, 1 0, 1 0, 1 0, 1 0, 0 1 and 1 1. Okay, so that would represent your code word. In that way, every sequence from start node to finish node. Okay, so you can actually call this the start, and you can call this the end or finish node. So every path from start node to end node gives you a code word. So this is another description of the trellis of the convolutional code, and actually it turns out that this is a very convenient starting point for describing decoding techniques for the convolutional code. In particular, most of you would have already heard of the famous Viterbi algorithm for decoding a convolutional code. Once you look at this graph, it's very easy to actually understand the decoding algorithm. So what we'll do next time is we'll actually continue this discussion on the trellis by actually using it to decode the code, assuming it's actually used for a binary symmetric channel. And beyond that, we'll actually continue our discussion to first include the general class of convolutional codes, and also we'll actually show how convolutional codes can be used over the additive Wert Gaussian noise channel as opposed to just the binary symmetric channel. So I think our time is almost up, so I'll stop here. Thank you.